All right, let's look at how to implement our regularized regression algorithms. So when we do this, we use the same linear regression that we saw earlier in our linear regression module, but we're going to add two new parameters. We're going to add mixture, and mixture can equal 0, it can equal 1, or it can equal any value in between. Okay, so when mixture equals 0, that is actually performing a ridge regression penalty. When mixture equals 1, that's going to perform a lasso. And when it's anywhere in between 0 and 1, let's say 0.5, we're actually doing an elastic net, a combination of both ridge and lasso. Now the penalty value, here it's 1,000, the penalty is equal to that lambda parameter that we saw earlier in those equations. So this is just regulating the size of the penalty that we're going to apply. And how we determine that size, we'll talk about that later on. Just realize that that is what it's doing. Now, what we're going to do here is we need to change the engine, right? We need to change to use what's called GlimNet. And GlimNet is a package that was the original implementation of regularized regression. And you can actually do regularized regression for linear regression models, for logistic regression models. We'll see an example of a logistic regularized model a little bit later on. But then there's also other options like a multinomial regression model and some others. Okay, so it's very flexible. And GlimNet is actually extremely efficient in fitting what we call the entire lasso or elastic net regularization path. The procedure to compute the regularized parameters can be quite costly, and GlimNet is very efficient. So you will almost always see GlimNet be the preferred engine we want to use for doing regularized regression models. All right, so we have our linear regression model now where we've added our mixture, our type of penalty, which is ridge, lasso, or elastic net, and then the size of the penalty, which is equal to that lambda. Now, one thing to note is that since regularized regression is basically computed with some equation or summation of the coefficients, we need to make sure that the coefficients are all based off of on a similar scale. Okay, and how we do that is we need to make sure that our actual predictor variables are based on the same scale. So we need to normalize, right, or standardize all our numeric predictors so that they have a mean equal to 0 and a standard deviation of 1. That puts all our numeric predictors on the same scale. And then we need to also dummy encode or do some kind of encoding to our non-numeric predictors. So in the previous modules, we saw that linear regression, logistic regression will actually dummy encode our categorical variables for us if we don't explicitly state it. GlimNet will not. So we need to actually add a step to do some kind of encoding of our categorical features to make them numeric. So in this case, we're just going to use dummy encoding. We could go through a different process of using one-hot encoding, or maybe we want to ordinal encode our basically all our numeric or nominal features that are on some kind of ordered scale, right? Like the rating, quality rating from poor to excellent. All right, but we do need to do this. Now, once we've done our feature engineering, then we can go ahead and apply the same procedure that we've seen in the previous modules, where we use a workflow object to add our recipe and also our model. And then we fit our workflow on our training data. We'll see in a little bit how we can actually use the cross-validation procedure, but for right now, we're just fitting it directly on our training data. Now, here we can extract our coefficients by using this extract fit parsnip and then tidy our model. So what this ends up doing is it pulls out our coefficients. Now here, how we interpret our coefficients is a little bit different before, because recall that we have scaled these or we have standardized them. So for example, here where it says year built 4,962. So rather than say for every 1 year newer a home is, that we expect an increase in the estimated sale price of 4,962. Here, what this is saying is for every one standard deviation greater than the average year that a home is built, that we have an increase in our estimated sale price of 4,962. Right. So, just important thing here to note is we have a slightly different interpretation of the coefficients once we have standardized them than we would otherwise. Now, if we were to look at our coefficients a little bit more closely, right, we could see here that we're going to have some coefficients that are extremely large. So here we just extract our coefficients and we arrange them in descending order based off of the absolute value of the estimates, coefficients. So now we're going to see that we have some coefficients that are extremely large. This is the intercept, but some of these other ones are on predictive variables. So you will see that these are all coefficients that were allowed to become very large because using them, we saw an equal or greater decrease in the sum of squared errors, right? So these are coefficients that our model is finding are very influential in actually having accurate predictions. Now, what we also will see if we were to come over here, and in this case, we arrange in the absolute value of estimates, but in ascending order, we'll see that some of these coefficients, here it says 0, but basically they are very close to 0. We're using a ridge regression model, so it doesn't actually push these to 0, but they're so small that it just registers as 0 in this printed output. Right, so these are very small coefficients that our model is identifying as being non-important, and that is why our ridge model has pushed these coefficients to basically equal to 0. And as we've done in the previous modules, we can do the same thing here. We take a workflow object, we add our recipe, we add our ridge model, and then we're going to fit on the k-folds that we create up here. So now we're going to do cross-fold validation so we can get our expected generalization RMSE value, which is 31,373.